Bismillahirrahmanirrahim. Welcome everyone. So today we will talk about chapter 22, Gauss's law. In Gauss's law, we will study the use of the electric field at the surface to determine the charge within the surface. We will learn the meaning of electric flux and how to calculate this electric flux. And we will learn the relationship between electric flux through surface and the charge within this surface. Let's start by the introduction. In chapter 22, the concept of electric field lines is described qualitatively. And for electric dipole, we can see the electric field lines are outward from the positive charge inward to the negative charge. The number of lines leaving the positive charge is equal to the number of lines entering to the negative charge. In this chapter, we will use the concept of electric flux to describe the electric field lines quantitatively. The electric flux can be represented by the number of lines, the number of electric field lines penetrating some surfaces. If we take a charge Q inside any surface S1, S2, or S4, S3, and these surfaces are a spherical surface for S1 and a regular surface for S2 and S3, we can say that the number of electric field lines is proportional to the magnitude of charge regardless the shape of the surface. As we said, S1 is a spherical surface, S2 and S3 are irregular shaped surfaces. If the surface encloses the charge, the net number of lines that go through the surface is proportional to the net charge inside this surface, regardless the shape of the surface. So we can say that the electric flux 1 through the surface, the spherical surface S1, is equal to the electric flux phi 2, phi 3 through the irregular shaped surface. Let me talk a little bit about something that we call vector area. The vector area, in a short definition, is a vector perpendicular to the surface or to the plane where its magnitude is equal to the area of the plane. Let's take a plane surface in the space has an area and has an orientation. Could be expressed, could this plane surface could be expressed by a vector area A? A vector area, as I said, has a magnitude which is equal to the area of the plane and has a direction which is perpendicular to the surface area, to this surface. A vector area can be written as the following: a vector A equal the magnitude, that means the area of the plane multiplied by a vector n. This vector n is a unit vector perpendicular to the surface and it's called normal vector. For any surface, n is defined locally at specific point. For closed surface, A is always directed outward. It's okay? So let me summarize here. A vector area is the area, the magnitude, multiplied by the unit vector. This unit vector, of course, because its name is unit, so its magnitude is 1, okay? But this area, for example, the area of the surface area of the sphere, how much? Yes, it's 4 pi r squared. For the cylinder, it's 2 pi r l. Good. So this is the surface area of some specific shape. And for example, that's all. I think it's enough. Now let's move to the electric flux. For the case 1, E is uniform, A is rectangular surface. The electric field lines are perpendicular to the surface, to the plane surface. In this example, we can see that this is the surface area and the electric field penetrating that surface are perpendicular to this to the plane surface. Okay, so we can see that the number of lines per unit of area is proportional to E, sorry. So we can define the product between the electric field and the area is called the electric flux phi. So what is the electric flux phi? The electric flux phi is E dot A. Okay, the product between the electric field and the area. This is when we are talking about a regular shape. That means we have a rectangular surface, and in a specific condition when the electric field lines are perpendicular to the surface. So we have two conditions. The first condition is a rectangular surface. The second condition is the electric field lines are perpendicular to the surface of the plane. What's the unit of the electric flux? As you know, the unit of the electric field is a Newton per Coulomb, and the unit of the area is meter squared. So the unit of the electric flux will be Newton meter squared per Coulomb. Let's take other case. Case 2, the surface is not perpendicular to the field. In this case, and in a summary, the electric flux will be phi equal EA cosine theta. We will take into consideration the angle between the normal to the surface, that means the normal vector, and the orientation of the electric field, direction of the electric field. We will take into consideration, this is theta. Theta, I have to mention here, theta, it's not between the electric field and the surface of the plane. No, it's between the electric field and the normal to this plane. Okay, what is the definition of the magnitude of the vector multiplied by the magnitude of the second vector multiplied by cosine of the angle between them? Of course, it's the dot product. So for a regular surface with a non-perpendicular electric field to the surface, the electric flux in this case is expressed as the following: E dot A. That means EA cosine theta. Okay, and this equation is more general than the first one, because in the first case we took it like a special case when the electric field lines are perpendicular to the surface. Now the electric field is not perpendicular; it make an angle theta with the normal of this surface. Okay, case 3, surface is perpendicular to the field. And the normal to the plane of the surface, area A, is at an angle 90 degrees. Okay, this is the vector area, and this is the normal vector. What's the angle between the normal vector and the electric field? Of course, it's 90 as mentioned here. Okay, so what will be the electric flux according to the last expression, EA cosine theta? It will be EA multiplied by cosine 0. That means cosine 90, sorry, cosine 90. Cosine 90, as you know, it's 0. So the electric flux here in this case is 0. And you can see that there is no electric field penetrating this surface. No electric field penetrating this surface, and we said that the electric flux is proportional to the number of the electric field penetrating that surface. If the number n is 0, that means the electric flux is 0. Why? Because the normal vector is perpendicular to the electric field. Another case 4, the electric field is not uniform in this case, and the surface is irregular. You see that in the previous cases, we have regular shape. That means we can calculate easily the surface area of this shape. But now we will talk about non-uniform electric field. That means the electric field depends on the location, and the surface is irregular. That means we cannot easily calculate the surface area. What we're gonna do, it's similar like we did with the electric field produced by irregular shape. We will divide the surface into large number of small elements, each of an area delta A. Okay, We will divide this surface into small portions of area. And then the vector delta A is a vector whose magnitude represents the area of nth element. That means we will divide into small portions, many small portions of delta A, and then the electric field E can be described constant on this small element. We have electric field in this element, and we have surface area for this element. What we're gonna do in this case, phi will be, it will be what? It will be the dot product between E delta A. But what I said here, into small elements. So let's write here EI, delta EI, delta AI, and the limit of delta A tends to the 0. So what we can say about this equation, about this form, it will be only the integration of E dA. Okay, so from one side the electric field is the electric flux, it's equal E dot A when we have electric field uniform and regular shape. Now in general the electric flux will be this equation, the integral of EdA. And what means this 0, this in the integral? This means that the electric flux through a closed surface. Through closed surface. And that's all. This is what we can say today for this electric flux. Okay? That's all. This is the definition of the electric flux. For irregular shape and non-uniform electric field, we take an example. A disk with a radius 0.1 meter is oriented with its normal unit vector n at 30 degrees to the uniform electric field. So at first, we have regular or irregular shape. We have regular, a disk. What is the surface area of the disk? It's pi r squared. Good. In this case, what will be the flux? The flux is EA cosine theta. Good. What do you know about theta? Theta is the angle between the normal and the electric field. In our case, theta is 30 degrees. Here, be careful. In this problem, we are in the best case when we have an idea about the angle between the normal vector and the electric field. But in some cases, they will not give us this angle. They will give us the angle between the surface of the disk and the electric field, not the normal to the disk. No, the surface of the disk. In this case, we will see some examples. Question A, what is the electric flux through the disk? The electric flux through the disk, we apply directly the formula. It will be E, that means E multiplied by A. A in our case, what I said, it's pi r squared multiplied by cosine theta. Cosine, that means cosine 30. That's all. So it will be electric field, how much? 2 times 10 power 3 multiplied by pi multiplied by r squared. That means 0.1 squared multiplied by cosine 30, and we can get the result. Okay, let's move to question B. What is the electric flux through the disk if it's turned so that N is perpendicular to E? N is perpendicular to E, so that means it's oriented in this direction, and the angle now it's 90 degrees. The electric flux in this case 2, let's say this is electric flux 1. Electric flux 2, it will be E multiplied by A, that means pi r squared multiplied by cosine 90. Cosine 90 gives 0, that means the electric flux is 0. In this case, no electric field is penetrating the surface of the disk, okay? Because the phi is 0. Question C. In question C, he said, what is the electric flux through the disk if N is parallel? So the third case, N is parallel to the electric field. So what's the angle between the electric field and the normal to the surface? In this case, theta 3, it will be 0. Okay, phi 3, it's E multiplied by A, that means pi r squared, multiplied by cosine 0. Cosine 0, as you know, it's 1, so we can write directly E multiplied by pi r squared. Okay, good. And we are in the best case when the maximum number of electric field lines penetrating the surface of the disk. We can say that this is phi maximum when theta equal 0. This is phi minimum. That means when theta equal 90. Good. And this is in between, when we have an angle between the normal vector and the electric field. And we are done with the first part. Okay, let's take another one. We consider uniform electric field E oriented in the x direction. Find the net electric flux through the surface of the cube of edge L oriented as shown. We have a cube. Of course, the cube has 6 faces. Okay, the electric field is oriented in the x direction. Let's talk about surface 3 and surface 4. The vector area is perpendicular to the surface and it's outward. So dA3 is perpendicular to the electric field. That means the normal vector 3 is perpendicular to the electric field. That means the angle theta 3 is 90. That means the electric flux phi 3 is, of course, it's 0. Why? Because cosine 90 is 0. Let's talk about this. Phi 4. The electric field is to the x direction. The normal vector is downward. The angle between them is 90 or negative 90 degrees. So that means phi 4 also 0. What about this surface area? Let's this area. Let's say this is 5. The angle between the electric field and this normal vector is 90 also. So phi 5 is 0. The other face, let's say this is 6. Phi 6 also, it will be 0. Why? Because the electric field and phi and the vector normal vector n6 is 90 degrees. So we can say that phi 6 also it's 0. So as a conclusion, phi 3 0, phi 6 0, phi 2 0, no, phi 4 0, phi 5 0. We have only we have phi 1 and phi 2. Phi 1, the normal vector, let's take another color, for example, green. Phi 1, the normal vector in this direction. The angle between the normal vector and the electric field is 0. Okay? So phi 2, it should be E dot A. E, the product between E and the surface area A. What about the first face, the normal vector in this direction, outward? What's the angle between the electric field, which is pointing to the positive x direction? So the angle here is 180. Cosine 180. Cosine 180 gives -1. So phi in this case will be minus EA. He's asking about the net electric flux. The net electric flux is the sum of all these fluxes. We have only 2 fluxes difference to the 0, E1, phi 1 and phi 2, but they have the same magnitude but opposite in the sign, so their sum will be 0. Okay, so what is the electric flux through this cube? Through this cube, the net electric flux through the surfaces of the cube is 0. It's okay? Good. Let's continue. We will take some other case. A fundamental law relating the net electric flux through closed surface and the charge enclosed by this surface is what is Gauss's law. So today we will talk in this part about Gauss's law. What is Gauss's law? Gauss's law gave a relationship between the net electric flux through a closed surface and the charge enclosed by this surface. It's okay. We will take a positive charge Q located at the center of the sphere with radius R. Owing to Coulomb's law, the electric field at this surface is KQ over R squared. But we will try to apply Gauss's law to get the same result. Okay? This is in the second step. What do we said about the electric flux? The electric flux, we said for irregular shape in general form, it's the integration through closed surface of the vector E dot the vector dA. That means E dA cosine theta. After some steps, we can conclude that the electric flux can be also expressed as the following: Q divided by epsilon naught according to Coulomb's law. Okay, so let's write here the electric flux. It will be from one side E dA, the dot product between the electric field and the vector area dA, the element vector area dA, and from the other side it will be Q enclosed or inside this closed surface divided by epsilon naught. We call this relationship Gauss's law. It's okay? Good. Let's continue. A net electric flux through closed spherical surface is proportional to the charge inside it. Of course, we said Q phi equal Q inside divided by epsilon naught. It's proportional to the charge inside. The net flux through closed spherical surface is independent on the radius R. The result is a consequence of Coulomb's law, as E is proportional to 1 over R squared and A is proportional to R squared because E equal KQ over R squared and A equal pi 4 over 3, 4 pi R squared, the surface area of the sphere. So we have 1 over R squared multiplied by R squared, so they will cancel each other. So the electric flux is independent on the R. So whatever the radius of the spherical surface, we have the same electric flux unless there is the same net charge inside the surface. Okay. So we can conclude that the electric flux is the same regardless the shape of the surface. Whatever the shape, we have spherical, we have irregular. Since we have the same charge inside these surfaces, so we have the same electric flux. So it's independent on the shape. Also, the point charge is located outside the surface now. The net electric flux through a closed surface that surrounds no charge. How much? It's, of course, it's 0 because phi is equal Q inside the closed surface divided by epsilon naught. If there is no charge, no flux, no net charge. I'm talking about net charge, not no charge, but that means sometimes there is charge, but the net charge is 0. Okay, let's take this case. I will explain this in more details. The electric flux through the surface S, it's Q1 divided by epsilon naught. Now inside this surface we will add some other charges, Q2 and Q3. The electric flux through S prime, it would be the sum of all these charges enclosed by the surface divided by epsilon naught. So that we are talking about Q net. So that means phi equal Q net. Yeah. The net charge inside the closed surface divided by epsilon naught. That's good. Okay. If there is no charge, of course, as we said, there is no electric flux. The net electric flux through any closed surface is equal to the net charge inside it. Here we are talking about the net charge. That means the sum of all the charges inside this surface, enclosed by this surface. Gauss's law can be always used to calculate the electric field of a system of discrete charges or continuous distribution having a symmetry. Okay, we will come back to this symmetry later. Okay, if the net flux through Gaussian surface is zero, in this case, what we can say, which of the following statements are true? The first one, there is no charge inside the surface. There is no charge inside the surface. Yes, it's true, but not necessarily it's correct. Yes, it's true, but not necessarily. Why? Because sometimes there is a charge. Imagine that we have positive charge and negative charge. The net flux, the net electric charge inside this closed surface, how much? Phi, it will be Q net inside the surface divided by epsilon naught. The net is plus Q minus Q divided by epsilon naught. In this case, we have zero. You see that the electric flux is zero, but we have a charge inside this surface. So we are talking about the net electric charge, not only the electric charge. Okay? Sometimes there is no charge, of course, there is no flux. And sometimes there is charge, but the net charge is zero. In this case, though, there is no flux. The net charge inside the surface is zero. Okay, good. This is what I'm talking about it. The electric field is zero everywhere on the surface. The electric field is zero everywhere on the surface. The electric field is zero everywhere on the surface. Who said that? Who said that the electric field is zero everywhere at the surface is not necessarily true. For example, we have here a point of charge out of the surface, and we have electric field penetrating that surface. Okay, it can be zero, yeah, when the number of electric field lines penetrating is equal to the number of electric field lines leaving that surface. In this case, the total flux is zero, but sometimes it's not always true. Yeah, it can be true, but not necessarily. The fourth proposition, the number of electric field lines entering the surface is equal to the number leaving it. So in this case, the flux is zero. Yes, it's true and always. Okay, so what we can say also, a spherical Gaussian surface surrounds a point of charge Q. Describe what happens to the flux through the surface if, one, the charge is triplet. Phi is what? Is Q inside divided by epsilon naught. If we multiply the charge by 3, of course, on the other side, we have to multiply the flux by 3. So the charge is triplet. That means the flux is also triplet. The volume of the surface is doublet. What we said in the previous slides? We said it's independent on the radius r. So if we double the volume, that means we will change at least the radius. In this case, there is nothing happened because the electric flux is independent on the volume. Nothing. The first one multiplied by 3. Nothing happens. The surface is changed to a cube. Nothing happens because we are only related to the charge inside this closed surface. Nothing happens. The charge is moved from one location to another location, but inside the surface. Nothing happened because we are only related to the charge inside, whatever its location. Okay, so we are done with this lecture. Let's move to some class activities. The first one, a Gaussian surface, one encloses and is centered at the point charge plus Q. On a point charge, a second spherical Gaussian surface, 2, of the same size also encloses the charge but not centered. Only we have one difference, that for the blue Gaussian surface, the charge is at the center. For the red Gaussian surface, the charge is not centered. The flux now, how is it compared between the fluxes of the two surfaces? Of course, we said that the flux does not depend on the location of the charge inside the surface, but it depends on the charge inside the surface. The two surfaces they enclose the same charge, so flux, it will be the same. Okay, it will be the same, and the answer is B. Let's move to another question. 2-point charge plus Q and minus Q are arranged as following. Through which closed surface is the net electric flux equal to the zero? Let's talk about the area A. Do we have any charge inside? Yes, we have. The net charge, is it zero? No, it's not zero. It's plus Q phi A. It's a plus Q divided by epsilon naught. There is charge and this charge is positive. Let's talk about the phi B. Phi B, we have a charge and this charge is negative, so minus Q divided by epsilon naught. Let's talk about phi C. Phi C, it encloses the two charges. That means plus Q minus Q divided by epsilon naught. We are talking about the net charge inside the surface, so it's zero. Let's talk about phi D. D, there is no charge inside it, so the electric flux is zero. And the number of electric field lines entering the surface D is equal to the number of electric field lines leaving to the same D, the same surface. So let's write N entering equal N leaving. So the electric flux in this case is zero. Okay, so the question through which closed surface is the net flux equal to the zero? So we can say for both C and D, for both C and D. Okay, last question of this lecture. The figure shows 6-point charges that all lie in the same plane. 5 Gaussian surfaces, S1, S2, S3, S4, and S5, each enclose part of this plane. And the figure shows the intersection of each surface with the plane. Rank these 5 surfaces in order of electric flux through them, from the most positive to the most negative. We will repeat the same steps like we did before. For the surface 1, no charge inside, so the flux is 0. For the surface 2, what is it? We have 9 microcoulomb, 5 microcoulomb, minus 7 microcoulomb. 9 plus 5 minus 7 microcoulomb divided by epsilon naught. So what will be the result? 9 plus 5, it's 14 minus 7, it's plus 7 microcoulomb divided by epsilon naught. Let's talk about phi 3. Phi 3, what is it? Yes, phi 3, we have 9 plus 1 minus 10. 9 plus 1 microcoulomb minus 10 microcoulomb, all of them divided by epsilon naught, so it's 0. 9 plus 1, 10, 10 minus 10 is 0. Phi 4, what is the surface 4? We have 8 microcoulomb minus 7 microcoulomb. 8 minus 7 microcoulomb divided by epsilon naught, so that means 1 microcoulomb divided by epsilon naught. What about phi 5? Phi 5 encloses all the charges, so we have 5 plus 9 plus 1. This is 10, 15. 15 plus 8, that means 23. 23 microcoulomb minus 17 microcoulomb. All of them divided by epsilon naught. 23 minus 17 gives, yes, gives what? Gives 5 microcoulomb divided by epsilon naught. So let's rank from the most positive to the most negative. We have 5 and we have 7. So phi 2 is 7, greater than phi 5, which is 5 microcoulomb, greater than phi 4, which is 1 microcoulomb, greater than phi 1 and phi 3. Phi 1, which is equal phi 3, which is equal 0. Okay, so this is the correct ranking of the electric fluxes through from the most positive to the most negative. And we are done with this part of chapter 2, electric flux. So in summary, we can say that the electric flux for uniform electric field through irregular shape, the flux is equal E dot A. That means that the magnitude of the E multiplied by the magnitude of the surface area multiplied by cosine of phi. And phi in this case is the angle between the normal vector and the electric field E. Okay, the flux through any closed surface, to any surface, whatever, if the electric field is uniform or the shape is not is irregular. In this case, the flux will be the integration of E dot dA. And like that, we introduce the Gauss's law. The flux is equal from one side, the integration through closed surface of EDA. From the other side, it's Q inside divided by epsilon naught. Thank you so much. Next lecture, we will talk about the Gauss's law and the applications of the Gauss's law. Thank you so much, and see you in the next